Hello, everyone. Welcome to part 2 of our series on NLU and IR. The screencast will be a crash course in classical IR, as well as evaluation methods in information retrieval. Let us first define the simplest form of our task, namely ranked retrieval. We will be given a large collection of text documents. This could be all of the passages in Wikipedia, perhaps a crawl of parts of the web, or maybe all of the documentation of Hugging Face or other software libraries. This corpus will be provided to us offline, that is, before we interact with any users, and we will be able to spend a one-time effort at organizing or otherwise understanding the content of these documents in the corpus before we start searching. Online, though, we will receive a query from the users, which could be a natural language question written in English, for example. The goal of our ranked retrieval system will be to output a top K list of documents sorted in decreasing order of relevance to the information need that the user expressed in the query. So this might be the top 10 or the top 100 results. So how do we conduct this task of ranked retrieval? As it turns out, we've already looked at a way for doing this before when discussing matrix designs. In particular, we know that we can build term document occurrence matrices. And in such a matrix like the one shown, each term document pair has a corresponding cell in which the matrix will store the number of times that the term appears in the document in our corpus. Of course, we will probably want to apply some sort of reweighting here, because we don't want to work with these row counts. But once we've done that, we can already answer queries that contain just a single term pretty well. And to do that, we would basically just return the K documents with the largest weight after normalization or other processes for this single term. And again, as it turns out, this is precisely what is done in classical IR if we have just a single query, just a single term in our query. When we have multiple terms in the same query, classical IR tends to treat them independently. So we would basically add the weights up across all of the terms in the query per document, and then that's the score for the document. This is precisely the computation that's shown here, where we compute the relevance score between a query and a document. We would go over all the terms in the query and simply add the corresponding document term weights for all of these terms for that document. This gives us a score for the document, and we can then return the K documents with the largest total scores. Interestingly, this reduces much of classical IR, though of course not all of it, to thinking about how do we best weigh each term document pair, which has an undeniable similarity to our first task this quarter in homework 1. Except of course that here in IR, we look at term to document relevance and not word to word relatedness. So thinking about term document weighting, here are some intuitions that might be useful as we think about what makes a strong term weighting model in IR. Of course, later in the next screencast in particular, we'll be looking at neural models that go beyond this. But for now, perhaps the two most prominent intuitions for term document weighting are connected to our first unit's discussion of frequency and normalization. In particular, if a term T occurs frequently in document D, the document is more likely to be relevant for queries that include the term T, or so is one of our intuitions. In terms of normalization, if that term T is quite rare, so if it occurs in only a few documents overall, we take that as a stronger signal that document D is even more likely to be relevant for queries including T. Lastly, if document D is rather short, we take that as also yet another signal that might increase our confidence that the term T was included in that rather short document for a reason. Taking a step back and thinking more broadly, we're still functioning under the same statement from the first unit. Our goal is ultimately to amplify the important signals, the trustworthy and the unusual, and to de-emphasize the mundane and the quirky. There are so many different term weighting functions in IR but most of them are directly inspired by TF-IDF and take a very similar computational form. For TF-IDF, this is a slightly different version to the one used in Unit 1. What I have here is slightly different. This is the more popular version in the context of IR applications, but TF-IDF is overloaded frequently, and you will see multiple implementations if you go look for them. So we'll define N to be the size of the collection, and DF, or document frequency of a term, DF of term, to be the number of documents that contain that term in the collection. Then TF, or term frequency, of a term document pair will be defined as the logarithm of the frequency of this term in this document, with 1 just for mathematical reasons. IDF, or inverse document frequency, is defined as the logarithm of N divided by the document frequency of the term. TF-IDF is then nothing but the product of these two values for each query term, summed up at the end to assign a single overall score to each document by summing up across all query terms, as we've discussed before. Of course, higher scores are better, and the top K scoring documents are those that we would return to the searcher if we were to use TF-IDF. Notice how both TF and IDF grow sublinearly, and in particular logarithmically, with frequency and 1 over DF, respectively. A much stronger term weighting model in practice is BM25, or best match number 25. And as you might imagine, it took many attempts until BM25 was developed. For our purposes, unlike TF-IDF, term frequency in BM25 saturates towards a constant value for each term, and also it penalizes longer documents when counting frequencies, since a longer document will naturally contain more occurrences of its terms. These are the main differences, and it really helps BM25 in practice be a much stronger term weighting model. Now that we've decided the behavior of these weighting functions, or at least a couple of them, how would we actually implement this as an actual system that we could use for search? So let's think about this. Whereas the raw collection, the actual text, supports fast access from documents to terms, so basically tokenization gives us the terms of each document, the term document matrix that we've studied so far allows fast access from a term to the documents. So it's a bit of the reverse process. Unfortunately, the term document matrix is way too sparse and contains too many zeros to be useful, since the average term does not occur in the vast majority of documents, if you think about it. So the inverted index, that's where it comes in. This is a data structure that solves this problem. It is essentially just a sparse representation of our matrix here, which maps each unique term in the collection, so each unique term in our vocabulary, to what we call a posting list. The posting list of a term T simply enumerates all of the actual occurrences of the term T in the documents, recording both the ID of each document in which the term T appears, and also its frequency in each of these documents. So beyond term weighting models, IR, of course, contains lots of models for other things. So there are models for expanding queries and documents. This basically entails adding new terms to queries or to documents or to both to help with the vocabulary mismatch problem that we discussed in the first screencast of the series. Basically, when queries and documents use different terms to express the same thing. There's also plenty of work on term dependence and phrase search. Notice that so far we've assumed that terms in each query and in each document are independent, and we functioned in a bag of words fashion. But work on term dependence and phrase search relaxes these assumptions that each query is a bag of independent terms. Lastly, there's also lots of work on learning to rank with various features, like how to estimate relevance when documents have multiple fields, like maybe a title, a body, some headings, a footer, and also anchor text, which is a very strong signal when you have it, like in web search. So this is basically the text from links in other pages to your page. The text in those links or around those links tends to be very useful as a relevance signal. And of course, also things like PageRank with link analysis and lots of other features for IR like recency and other stuff. But I think it's worth mentioning that until recently, if you just had a collection that you want to search and you didn't want to do a lot of tuning, BM25 was a very strong baseline on the best that you could do ad hoc. So without lots of tuning and without lots of training data, etc. And this only changed a year or two ago with the advent of BERT-based ranking, which we'll discuss in detail in the next screencast of the series. Okay, so we just built an IR system. How do we evaluate our work? What is success like? Well, a search system, as you can imagine, must be both efficient and effective. If we had infinite time and infinite resources, we would just hire experts to look through all of the documents one by one to conduct the search. But clearly, we don't have that sort of ability. So efficiency in IR is paramount. After all, we want our retrieval models to work with sub-second latencies for collections that may have hundreds of millions of documents, if not even larger than that. The most common measure of efficiency in IR is latency, which is simply the time it takes to run one query through the system, say on average or perhaps at the tail, like the 95th percentile, for example. But you can also measure throughput in queries per second, space, how much, maybe the inverted index takes on disk versus, say a term document matrix. How well do you scale to different collection sizes in terms of the number of documents or the size of the documents? And how do you perform under different query loads? Many queries, few queries, short queries, long queries. And lastly, of course, what sort of hardware do you require? Is it just one CPU core, many cores, a bunch of GPUs? But latency tends to be kind of, once you've determined the other ones, it's the go-to metric in most cases. More central to our discussion today, and we'll focus on this for the rest of the screencast, is IR effectiveness, or the quality, basically, of an IR system. And here we ask, do our top K rankings for a query satisfy the user's information need? Answering this question tends to be harder than evaluation for typical machine learning tasks like classification or regression, because we're not really just taking an item and assigning it a class. We're trying to rank all of the items in our corpus with respect to a query. In practice, if you have lots of users, you could run online experiments where you basically give different versions of your system to different users and compare some metrics of satisfaction or conversion, basically in terms of purchases or otherwise. But for research purposes, we're typically interested in reusable test collections that allow us to evaluate IR models offline and then compare them against each other. Building a test collection entails three things. First, we need to decide on a document collection, our corpus, a set of test queries, and we need to find or get or produce relevant assessments for each query. If resources permit, a collection could also include a train-dev split of queries, but given the high annotation cost, it's actually not uncommon in IR to find or create only a test set. The key component of a test collection is the relevant assessments. These are basically human annotated labels for each query that enumerate for us whether specific documents are relevant or not to that query. These query document assessments can either be binary or they could take on a more fine-grained, graded nature. An example of that is grading a query document pair as -1, 0, 1, or 2, with meanings of, hey, this is a junk document, -1. You should not retrieve it for any query, or this document is irrelevant, but it might be useful for other queries, or this document is quite relevant for this query, but it's not a perfect match, or here is a really, really good match for our query, which would be a score of 2 or 3, depending on the grades that you're using for the assessments. As you might imagine, because we work with potentially many millions of documents, it's usually infeasible to judge every single document for every single query. So instead, we're often forced to make the assumption that unjudged documents are not relevant. or at least to ignore them in some metrics of IR, though for most purposes they are treated as not relevant. Some test collections take this further and only label 1 or 2 key documents per query as relevant and assume everything else is not relevant. So this tends to be useful when you work with particular data sets, and you want to keep it in mind as you do evaluation. So many of the test collections out there in IR are annotated by TREC, or the Text Retrieval Conference, which includes annual TRECs for competing and comparing IR systems. For instance, the 2021 TREC conference has TRECs for search in the context of conversational assistance, health misinformation, fair ranking, and has a very popular deep learning TREC as well, which we'll discuss in more detail. Each TREC campaign emphasizes careful evaluation with a very small set of queries. So just 50 queries is a very typical size, actually. But TREC extensively judges many, many documents, possibly hundreds of documents or even more for each query here. So you can imagine an alternative, which we'll look at next, where you have lots of queries, but you only judge a very small number of key documents for those queries, with the intention that the performance that you get will average out over a large enough set of queries. And this is exactly what happens in MS Marco ranking tasks, which is a collection of really popular IR benchmarks by Microsoft. MS Marco contains more than 500,000 Bing search queries, and this is the largest public IR benchmark. Each query here is assessed with 1 or 2 relevant documents, and we assume everything else is not relevant. And having this sparse annotation is often not a problem at all for training because we have so many training instances. And so MS Marco provides a tremendous resource for us when it comes to building and training IR models, especially in the neural domain. It also turns out that sparse labels are not too bad for evaluation either, especially because of the size of the test queries. We can use many thousands of test queries and average our results across all of them to get a pretty reliable signal about how different systems compare. There are multiple test collections out there on top of MS Marco. So there's the original passage ranking task, a newer document ranking task where the documents are much longer, but there's fewer of them. And then there's also the TREC deep learning track, which we've mentioned before, which is happening every year since 2019, and which uses the MS Marco data, especially for training mostly, but has far fewer queries for testing, with lots more labels for evaluation, a lot more extensive assessments and judgments for evaluation. So these are much denser labels. There are also plenty of other rather domain-specific IR benchmarks, many of which are collected in this table by Nandan et al. In a very recent preprint. As you can see, these benchmarks vary greatly in terms of the training size, if there is any training at all, the test set size, the average query length, the average document length, and many other factors. BEAR, or Benchmarking for IR, is a recent effort by Nandan et al. Here to use all of these different data sets for zero-shot or out-of-domain testing of IR models. Specifically, in BEAR, we take already trained IR models that do not have access to any validation or training data on these downstream IR tasks and test them out of the box to observe their out-of-domain retrieval quality. So that is without training on these new domains. Okay, so we now have a test collection with queries, documents, and assessments. How do we compare IR systems on this collection? First, we will ask each IR system to produce its top K ranking, say its top 10 results, and we'll use an IR metric to compare all of these systems at that cutoff K. The choice of IR metric and the cutoff K will depend entirely on the task. So I will briefly motivate each metric as we go through them. All of the metrics we will go through are simply averaged across all queries. And so to keep things simple, I will show the computation of the metric for just one query in each case. But you want to keep in mind that this is averaged across queries. Let us start with two of the simplest IR metrics, which are success and MRR. For a given query, let rank be the position of the first relevant document that we can see in the top K list of results. Success at K will just be 1 if there's a relevant result in the top K list, and 0 otherwise. This is a very simple metric, as you can see, that can be useful in cases where we assume that the user just needs one relevant result anywhere in the top K. And in particular, it can be useful if our retrieval is fed to a downstream model that looks at the top K results and then does something with them. So it can read all of them, and it will read all of them anyway. So we're just interested in binary relevance here. Mean reciprocal rank, or MRR, also assumes that the user only needs one relevant query in the top K, but it assumes that the user does care about the position of that relevant document in the ranking. So a relevant document at the second position, for example, is only given half of the weight of a relevant document in the top position. You're probably already familiar with precision and recall, but let's define them here in the context of top K ranked retrieval. For a given query, let ret of K be the top K retrieved documents, that set of top K retrieved documents. And let rel be the set of all documents that we judged as relevance as part of our assessments. In this case, precision at K is just a fraction of the retrieved items that are actually relevant. And recall at K is the fraction of all relevant items that are actually retrieved. A pretty popular metric is also MAP, or mean average precision, or just average precision for one query, which essentially brings together notions from both precision and recall. To compute average precision for one query, we will add up the precision at I for every position I from 1 through K where the ith document is relevant. We will divide this whole quantity by the total number of documents that were judged as relevant for this query. All of the metrics that we've considered so far only interact with binary relevance. That is, they just care whether each document that is retrieved is considered relevant or not relevant. DCG, or discounted cumulative gain, works with graded relevance. So for instance, 0, 1, 2, and 3. For each position in the ranking from 1 through K, we will divide the graded relevance of the retrieved document at that position by the logarithm of the position, which essentially discounts the value of a relevant document if it appears late in the ranking. Unlike the other metrics, the maximum DCG is often not equal to 1. So we can also compute normalized DCG, or NDCG, by dividing for each query by the ideal DCG. This is obtained basically if all of the relevant documents are at the top of our top K ranking and they are sorted by decreasing relevance. So all of the 2s before all of the 1s before all of the, the 0s in this case that are not relevant. All right, having discussed classical IR and evaluation in this screencast, we will focus on neural IR and in particular state-of-the-art IR models that use what we've learned so far in NLU in the next screencast.